By 2030, the Indian Ministry of Defense intends to transform the country into a global hub for unmanned aerial systems, scaling production to meet both civilian and military requirements. For decades, military power was calculated through platform-centric dominance, a single advanced fighter, tank, or warship designed to control its operational domain. That equation is now inverting. The disruption lies in scalable combat power. Small, inexpensive autonomous systems operate in high-volume saturation formations, overwhelming traditional defenses through sheer numbers rather than individual sophistication. This creates a structural deficit in defense economics. When a drone costing a few $1,000s forces the expenditure of a surface-to-air missile worth millions, the financial burden of defense rapidly exceeds the cost of the attack. Along India's borders, adversarial inventories are rapidly expanding to exploit this asymmetry. Both China and Pakistan are scaling their capabilities from basic tactical UAVs to long-range loitering munitions. Legacy anti-access and area denial networks, built primarily to track and intercept conventional aircraft, are highly vulnerable when subjected to continuous probing and mass saturation by these expendable systems. Future conflicts will initiate with waves of unmanned systems rather than armored columns. New Delhi's strategic response requires a multi-miter autonomous ecosystem capable of both absorbing and projecting mass. The Chanakya framework operates as a decentralized UAV swarm autonomy framework, governing multiple platforms through local logic rather than a central airframe. Traditional operations rely on a hub-and-spoke model. Aircraft depend on a central controller, creating a vulnerable node. Chanakya enables distributed decision-making. Drones process data locally, forming a mesh network. In electronic warfare, if one unit is destroyed, the swarm reconfigures to maintain mission integrity. The framework dynamically assigns operational roles without human input. Individual platforms adapt their behavior in real time, serving as forward scouts, radar jammers, decoys, or kinetic strikers based on the immediate tactical requirement. Localized processing compresses the sensor-to-shooter loop from minutes to seconds. India offsets a numerical disadvantage by establishing superiority in cognition. While swarm mass handles the tactical layer, high-altitude penetration requires a different architecture. Modern integrated air defense systems make it difficult for conventional manned aircraft to enter contested airspace without detection. India's strategic response is the DRDO Ghatak, an unmanned combat aerial vehicle designed specifically to execute deep strike missions inside heavily defended enemy territory. Constructed from carbon composite materials, the airframe reduces weight for payload endurance while absorbing incoming radar waves. Utilizing a flying wing geometry and internal weapons base, it eliminates vertical tails and external pylons that reflect radar signals, maintaining an exceptionally low signature. This allows the Ghatak to bypass early warning networks and position precision-guided munitions directly over high-value strategic targets, including command nodes and logistical hubs. Combining stealth geometry with autonomous navigation provides New Delhi with long-range strike autonomy. It allows India to project offensive power into hostile airspace without exposing human pilots to unacceptable risk. This capability merges into the doctrine of distributed air combat. In this model, manned fighter aircraft remain outside the most contested zones, functioning as command nodes that control forward-deployed networks of unmanned assets. The Svayat M1 serves as the AI-enabled loyal wingman in this formation. It functions as a force multiplier that can conduct forward reconnaissance, execute electronic warfare, or absorb enemy fire to protect the primary manned platform. Beneath the stealth and wingman layers sits the tactical tier of loitering munitions. Indigenous programs like Project Call and Sheshnag 150 are designed for deep penetration strikes, offering ranges exceeding 1,000 kilometers. These systems operate on a dynamic targeting loop. Rather than flying to predefined coordinates, they remain airborne for hours to scan complex terrain, track mobile assets, and wait for the optimal tactical window to strike. Flying at low altitudes with minimal radar cross-sections, these munitions bypass conventional detection. They cost a fraction of traditional cruise missiles, allowing them to be deployed in overwhelming numbers. Integrating stealth combat vehicles, loyal wingmen, and scalable loitering munitions creates a complete combat ecosystem. This multi-layered architecture inverts the economics of aerial warfare, shifting the financial burden of interception entirely onto the adversary. Global military planning increasingly assumes that the rise of artificial intelligence and robotics will result in smaller, heavily contracted armed forces. For India, this assumption fails. The geographic reality of a dual front border and extreme topographic diversity demands a different strategic posture. There is a rigid operational distinction between projecting kinetic power through a technological platform and physically holding contested territory over time. Operations spanning counterinsurgency and border management in theaters like the Himalayas require continuous physical presence. The terrain necessitates massed infantry that can operate where machines suffer severe degradation. Autonomous technology executes reconnaissance and precision strikes without the capacity to occupy and secure mountainous ground above 16,000 feet. The Himalayan theater imposes severe aerodynamic constraints on aviation. The thin air reduces engine power and rotor efficiency, sharply limiting the weapon payloads of conventional helicopters. To solve this, Hindustan Aeronautics Limited developed the HAL Prachand, an attack helicopter specifically optimized to maintain lift and maneuverability during combat operations above 15,000 feet. The Prachand is currently integrating into the wider drone ecosystem, evolving into an airborne command node for networked strike operations. Planners are adapting the helicopter to serve as an airborne launch platform. Rather than exposing the aircraft to ground fire, the crew can deploy loitering munitions directly into narrow, heavily defended mountain valleys. This capability extends the pilot's strike range far beyond the reach of conventional anti-tank guided missiles, allowing the crew to disengage while the drone autonomously tracks and destroys the target. In the WFI doctrine, autonomous systems serve as force multipliers that scale military reach while preserving the essential requirement for human mass and territorial control.